Hello students, in this video we will be discussing alpha decay in detail. Here we include the tunnel theory of alpha decay and the derivation of decay constant. Now, alpha decay is impossible in classical physics. It nevertheless occurs. According to classical theory, alpha decay was an impossible process because the attractive forces between the nucleons are of very short range. Right? The total binding energy in a nucleus is approximately proportional to the mass number, the number of nucleons it contains, okay, which we have dealt earlier in liquid froth model. But the repulsive electric forces between protons, however, are unlimited, and this disruptive energy in a nucleus is approximately proportional to Z square, which is the Coulomb energy. So there are two forces existing, the attractive force and the repulsive electric force. So nuclei which contains 210 or more nucleons are so large that the short-range nuclear forces that hold them together are barely able to counterbalance the mutual repulsion of their protons. So nuclei which has 210 or more nucleons has the nuclear force or the short-range attractive force couldn't counterbalance the mutual repulsion of their protons' disruptive energy or the repulsive Coulomb energy. So, alpha decay occurs in such nuclei as a mean of increasing their stability by reducing their size. Okay. Now, why are alpha particles emitted rather than, say, individual protons or He2 3 nuclei? Why alpha particle is always emitted, not such nuclei or protons are not emitted? The answer follows from the high binding energy of alpha particle. Because of the high binding energy of alpha particles, such a particle is emitted. Right? To escape from a nucleus, a particle must have a kinetic energy, and only the alpha particle mass is sufficiently smaller than that of its constituent nucleons for such an energy to available. So, the mass defect which gives them enough kinetic energy for the particle to escape from the nucleus, that is possible, that is only available for alpha particle. That is why alpha particles are emitted rather than any other type of particles are not emitted. Now we find the disintegration energy. This is the energy released when various particles are emitted by a heavy nucleus. Okay, Q is equal to this Mi is the mass of initial nucleus, Mf is the mass of final nucleus, and Mx is the particle mass. Which particle is escaped from the nucleus? The mass of that particle is Mx. So the disintegration energy Q is equal to Mi minus Mf minus Mx. So minus of Mf plus Mx. C square. This is the disintegration energy or the energy released when various particles are emitted by a heavy nucleus. Okay. Now the kinetic energy of alpha particle, Ke alpha, the kinetic energy of alpha particle is never quite equal to the disintegration energy because since the momentum must be conserved, the nucleus recoils like recoil of current. There should be a backward momentum which conserves. Right? The nucleus recoils with a small amount of kinetic energy when the alpha particle emerges. So, the kinetic energy of alpha particle is derived from the momentum and energy conservation, and we get it as Ke alpha is equal to approximately A minus 4 by A into the disintegration energy, where A is the mass number of the original nucleus or the parent nucleus. Okay. Now the mass numbers of nearly all alpha particle emitters, which has greater exceeds 210 number of nucleons. So most of the disintegration energy appears as the kinetic energy of alpha particle. Okay. It is of this equation form. K infinity. K kinetic energy of alpha particle is approximately equal to A minus 4 by A cube. Now try this problem in your notebook. Next is the tunnel theory of alpha decay. While a heavy nucleus can, in principle, spontaneously reduce its bulk by alpha decay, there remains the problem of how an alpha particle can actually escape. That is explained by tunnel theory. How an alpha particle can actually escape the nucleus. It is explained by the tunnel theory. So this is a case of a alpha particle. This is the classical picture and this is the quantum picture. It is a potential well and this shows the variation of potential energy of alpha particle. And this value is the kinetic energy of alpha particle. So in classical physics, an alpha particle whose kinetic energy is less than the height of the potential barrier around the nucleus cannot enter or leave the nucleus whose radius is R0. R0 is the nuclear radius and the particle energy is only this much and this is the height of the potential barrier. So alpha particle cannot escape by the classical approach, right? And this is the quantum picture. See, in quantum physics, such an alpha particle can tunnel through the potential barrier with the probability that decreases with the height and thickness of the barrier. So this is the explanation of tunneling effect of alpha particle. This here you can see the wave function of alpha particles outside this range. This is the nuclear radius and this is outside that range. You can see the alpha particle tunneling through the barrier. Right? We'll look into this in detail. So the plot was the potential energy U of an alpha particle as a function of its distance r from the center of a certain heavy nucleus. The height of the potential barrier is about 25 mega electron volt, which is equal to the work that must be done against the repulsive electric force to bring an alpha particle from infinity to a position adjacent to the nucleus, but just outside the range of attractive forces. So this much energy must be given or external work should be given in order to escape the alpha particle from the nucleus, since this is the height of the potential barrier. But we may therefore regard an alpha particle in such a nucleus as being inside a box, particle in a box, whose wall requires an energy of 25 mega electron volt. However, the decay alpha particle have energies only up to 4 to 9 mega electron volt. This is 16 to 21 MeV short of energy needed for escape. So even if it cannot escape, it can tunnel. So classically, theory of alpha decay can be explained. In 1928, Gamow, Gurney and Condon independently confirmed alpha decay by quantum mechanics. The basic notions of this theory were: an alpha particle can exist as an entity within a heavy nucleus. Okay. Second point is that such a particle is in constant motion and is held in the nucleus by a potential barrier. The third point is that, this is the important one, there is a small but definite likelihood or the probability that the particle may tunnel through the barrier despite its height, each time a collision with it occurs. So there is a definite probability that a particle can tunnel through the barrier. Okay, so according to this assumption, the last assumption, the decay probability per unit time, lambda, this is the decay constant, decay probability per unit time is given by nu into T, where nu is the number of times per second an alpha particle within the nucleus strikes the potential barrier around it, and T is the probability that particle will be transmitted through the barrier. So lambda is defined as nu into T. Nu is the number of times per second alpha particle collide with the barrier and T is the transmission probability. Now if we suppose that at any moment only one alpha particle exists as such in a nucleus, and that it moves back and forth along a nuclear radius, we find the collision frequency nu is equal to velocity v by 2r0, the total distance. R0 is the nuclear radius, where v is the alpha particle velocity and R0 is the nuclear radius. And we substitute these two, we get the collision frequency nu is approximately 10 raised to 21 second inverse. That means the alpha particle knocks all its confining balls 10 raised to 21 times per second, and yet we have to wait an average of such as 10 raised to 10 years to escape from some nucleus. Next is the tunnel theory for decay constant, the derivation. We consider a beam of particles of kinetic energy E was considered, which was incident on a rectangular potential barrier whose height is U, which is greater than E. E is the kinetic energy of alpha particle, and U is the potential barrier. U is greater than E. Now, an approximate value of transmission probability is T is equal to e raised to minus 2 K2L. What is T? It is the transmission probability is defined as the ratio between number of particles that pass through the barrier and the number that arrive. Ratio of the particles that pass through the barrier and the number that arrive. So this is the transmission probability, where the wave number K2 is the wave number inside the barrier is defined as K2 is equal to root of 2m u minus e by h cross. So when we take the equation for u for a rectangular potential barrier, whereas an alpha particle inside nucleus is faced with a barrier of varying height, so which we have seen in the above figures. So we take that equation and we first write that equation in this form. Ln T is equal to minus 2 K2L. Now then express it in terms of an integral. Ln T is equal to minus 2 integral 0 to n K2R dr. So the integration is from R0 to R, and small r is a variable, where R0 is the radius of the nucleus and R is the distance from its center at which U is equal to E. The kinetic energy E, when it is greater than the potential energy for small r greater than R, in such a case the alpha particle will have permanently escaped from the nucleus. Okay. Now the electrical potential energy between the nucleus of a charge Ze and that of alpha particle, which have a charge 2e, you get UR is equal to 1 by 4 pi epsilon 0 Ze into 2e, Ze into 2e by R. So Ze is the nuclear charge minus the alpha particle charge, or Z is the atomic number of the daughter nucleus. Okay, and we substitute u in this equation, you get like this, 2m by h cross all raised to half, substituted u minus e raised to half. So this is a variation of u, and this is the point at which u is equal to E, or the potential energy of the barrier is equal to the kinetic energy of the alpha particle. This point, you can see U is equal to E. Now, since U is equal to E when R is equal to R, you can substitute it like this. Okay, and you substitute for E, you get this equation K2 is equal to this form. Now we find Ln T is equal to, and substitute for K2. We go through the derivation. Now because of the potential barrier is relatively wide, R is much greater than R0, and so you can have an approximation like this, with the result that Ln T is equal to minus 2m e by h cross square raised to half R into pi by 2 minus 2 R0 by R raised to half. From the equation, R is equal to 2 ZD square by 4 pi epsilon 0 E. Substitute that in this equation for L and T, you get this relation. Okay. So here, these are all constants. A constant times Z raised to half R0 raised to half minus a constant into Z E raised to minus half. So on evaluating this and putting that constant, you get ln t is equal to 2.97 z raised to half r0 raised to half minus 3.95 z d raised to minus half. Where E is the alpha particle kinetic energy expressed in mega-electron volt. R0 is the nuclear radius. Z is the atomic number of the nucleus minus the alpha particle. Now, when we convert that into terms of logarithm, log 10 to a, log a to the base 10 is equal to log 10 e to the base 10 into log a, you get it as the value. And substituting that, you get log to the base 10 t is equal to 1.29 z raised to half r0 raised to half minus 1.72 z e raised to minus half. From the equation for the decay constant lambda is equal to nu t which I dealt earlier, where nu was v by 2 r0, v by 2 r0 into t. I'm substituting that, we take first of all, we take the logarithm on both sides and substitute the transmission probability. We get alpha decay constant log 10 log lambda to the base 10 is equal to log v by 2 r0 to the base 10 plus the transmission probability. Okay. This is the relation connecting alpha decay constant with the set, which is the atomic number of the daughter nucleus, and the kinetic energy of the alpha particle. Here is a graph with the variation of log lambda to the value of z e raised to minus half. For this white dots show the result, and we have fitted a straight line to this graph. Okay, from this straight line you can find the nuclear radius by this graph. That is the important result of this equation. You can find out the nuclear radius through the alpha particle alpha decay plot of log lambda to e raised to minus half.